So let's start with self and cross attention. But first, a brief history of transformer, why transformer came into picture, and what was so groundbreaking about that paper attention is all you need. So before transformers, we have two things. One was RNN, it was not that popular at that time, and the other one was LSTM, which was used a lot by the industries when transformer was coming into picture. Now what happened is that the issue with RNN and LSTM both was they had a problem called vanishing gradient. Now what does vanishing gradient means? Well, first of all, the transformer intentionally was brought into picture for sequence to sequence mapping task. Now sequence to sequence mapping, say for example, let's take an example of language translation. So I say I am a good boy. So this is a sequence of words in English language, and I want to map it into a French, whatever it comes out to be in French. So that is basically a sequence of words into English, which I'm translating into sequence of words into French. That is sequence to sequence mapping. Now the problem of RNN and LSTM was vanishing gradient. Vanishing gradient means that these models, they were not able to learn, they were not able to capture larger context. So if I increase the length of my sequence, which is length of my length of my sentence, so they will forget at some point of time that in what context I was talking about that particular sequence. So that was one of the issue. Actually, this issue was in RNN, for to overcome which LSTM was brought into picture. But again, then LSTM also suffered with vanishing gradient when you increase the context length to a larger extent. This was one of the issue. The other major issue was the issue of parallelization of code. Now, parallelization of code means that RNNs and LSTM both work sequentially. Sequentially means they will take one input, they will map it to another output. They will take input, they will map to output. And the input from the previous layer was also considered in producing output of the current layer. So this was one of the issue, that you can't parallelize your code. So transformer brought into picture it handled the issue of parallelization, which made the training of these models much faster. Now coming to this part. We talked about what are sequence to sequence model. Let's talk about what is self attention and what is cross attention. Just an overview, we'll go into details later. So the word self attention, intuitively it means that you are attending something onto oneself. So for example, let's talk about a sentence, I am a good boy. We'll go with this sentence through the entire slide. Now, I am a good boy. In this, I want to know what is the dependency. I mean, what is the relation between each of the word with every other word. So here the sentence is same, and I want to know the relation between every other word within the same sequence itself. I mean, modality is also same. By modality, I mean it is coming from text, it is coming from image, it is coming from audio, or from what. So modality is also same, and the input itself is same. So we don't have any other input. We just have one sentence, and we want to know what's the dependency between each of the word. Now, when you will start producing an output, so suppose the first word comes out to be I, so there is a very high probability that the next word should be am. This is what we have been taught in English, that I is mostly followed by am. So this is the dependency between I and am. So when you take the dot product of these two representation, it will come out to be very high after learning the representation. So that's what basically self attention tries to capture over here. Now what does cross attention tries to do? Well, the word cross itself means we are trying to bring two modalities into one. We're trying to capture dependency of two different things. So for example, let's say I have an image vector over here, I have a text vector over here. Now I have to know what's the relation, like how can I model my image based on text, or how I can model my text based on my image. So for that we'll use cross attention over here. Cross means two different modalities, same thing. Okay, so this is about an intuitive idea of self attention and cross attention. And this is the image from the paper itself of attention is all you need. And this is the architecture they proposed. This is your encoder, this particular section, and this is your decoder. We won't go into that because main motto focus on attention itself. Now let's come to self attention. I'm assuming that you know the concept of embeddings and how text is represented into vectors of words, and how this encoding is done using clip or any other of the encoder. I'm assuming that we are all good with it. So suppose we have an input. This is X, which I am considering as an input. Now its dimension is something R sequence length cross D model. D model is a hyperparameter that was mentioned in the paper. In paper they took D model to be 512. So R is a X is a matrix of length, sequence length cross D model. What we do, we create 3 same matrices out of there. So these 3 are pretty much same, pretty much not exactly same at this point of time. Now we project this particular X into some other dimension, and this projection is learnable. So when I say learnable projection, it means that we are applying a linear layer over here. Linear layer, so this is my linear layer. This is how basically when you create a linear layer, it creates a matrix. So if you have an X, so it will be some W transpose X plus B, by B is the bias and X is the input which you are giving, and this W is the learnable matrix over here. This W and B both are learnable, by the way. So this is the dimension of W that I have written. So I have 3 linear layers over here, which is query, key and value. So each of the dimension is D model, D model, D model, D model, D model, D model. We are learning about self-attention, so there won't be much issue in understanding what the dimension should I use. So it will be pretty much uniform across all the 3 layers, 3 linear layers, query, key and value. Now if you multiply X and WQ, I mean your output after applying this linear layer will be of again the same dimension. So this is what output is calling. I'm Q prime, K prime and V prime. So Q prime will be again will belong to R sequence length cross D model. Similarly, which will be equal in dimensionality. This Q, K, at this point X, X, X they were same, but here Q prime, K prime, V prime, these all will be a different matrices, but everyone's dimension will be same, and that dimension will be R sequence length cross D model. Cool. I hope we're clear over here. So this is my sequence length and this is my D model. So coming to the next part, now basically let's see about multi-added attention a bit later. Let's see self-attention in detail right now itself. Now how do we calculate self-attention? So this is the formula for attention. You have your query matrix, you have your key, and you have your V, Q, K, V. Here this is basically Q prime, this is basically K prime, and this is basically V prime after projection what we have over here. Now what we do, we first of all we take Q, K transpose by root DK, then we take softmax of it. We'll see why we are using softmax, and dot V. So this is the basically calculation of attention. This is the formula which was mentioned in the paper, and this I am pretty sure most of us are familiar with it. So that's how your attention is basically getting calculated. Now there are 2 things which we see, which I want to which I found that most of the videos are missing over here. The first one is softmax compulsory over here, and the second one is when you're applying softmax, along which dimension you should apply. So this QK transpose, Q is belonging to R sec length cross D model. Then K is also belonging to R sequence length cross D model. So when you will multiply Q and then when you take transpose of K and you multiply with Q, you will come with the matrix, let's say T, that will be of length. This will belong to R sequence length cross sequence length. Now you have 2 dimensions. Now this is a matrix. Now when you're applying softmax over here, along which dimension should you apply? Should you apply through row or should you apply through column? Now this is one of the issue which I find very difficult to see where it was getting applied in the paper. Let's see how we'll sort it out. Now what's happening when you're taking self-attention? So let's see. This is I am a good boy, and you are taking self-attention, so this same sentence will come along the column itself. I am a good boy. G, 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 G. Now technically or ideally this diagonal should be of highest value. Let's talk in the whatever score you are getting after doing the cross product, I mean dot product, this diagonal should be of the highest value. Cool. Now what you are trying to do, this is my this is my query. Query means I am querying something against something. Against is my key. In self-attention we have both the same queries and keys, so query and key. So what you're trying to do what you're trying to do is that you're trying to find what is the dot product of I with every other word. So at the end of the day, you want to find a probability along this dimension. Softmax basically give you probability distribution itself in a rough way. So what you want to do is you want to find the probability of I when getting a dot product with every other particular word. So it makes sense that you have to apply softmax along dimension 0. 0 is row wise, this one. So that's one detail which we missed over here. So this softmax will be applied along dimension 0. So you have applied softmax, and then it's pretty much same, the basic matrix multiplication what you do over here. Softmax applied, QKT transpose, and then V. Cool. So you first apply softmax and then you take, and this all these dots, these are not dot products, these are basically matrix multiplication. Now other is this is not actually dot product attention, this is another thing. This is what we call as scaled dot product attention. Scale dot product attention. Now why it is called scale? Because we are multiplying with 1 by root dk. Now again another question, why 1 by root dk? So see, this is the issue. This is something has to do with softmax activation function. So what is softmax? How? Now first of all let's talk about activation function. No, let's leave it that. So there is a minute difference between softmax and the sigmoidal activation function. Sigmoidal activation functions squashes the input within a particular range. If you're using logistic, so it's between 0 and 1 for a single input, but softmax does it for multiple inputs. So whatever input vector you give it, it will squash all those input vectors into the range of 0 to 1. This is the basic difference between sigmoidal and softmax activation function. And by sigmoidal I mean logistic, because if you see the tangent function, tan h function, it squashes the input between -1 to 1. So by sigmoidal, at this particular context, we mean by logistic sigmoidal function. So this is one of the thing. Now this is the graph of softmax. So if you see, this is softmax and this is my logistic sigmoidal activation function. Now the issue with both of these activation function is over this part. Let's change the color a bit. Over this part, this part. What's the issue in this part? Is the issue because here the derivative almost becomes 0. Now what happens when derivatives become 0? When derivative becomes 0, the learning stops, the gradient won't flow. So that's the issue. We are scaling by 1 by root dk, because if your dk is large, dk is basically, okay, let's assume that we are not using multi-headed attention for now. So if you're not using multi-headed attention, dk becomes d model. So if your d model is large, the query matrix which we generated, its size will be large. So whatever q dot k transpose you will get, it will be a larger matrix. And when the matrix become large, the softmax can go into this particular region. And when the softmax goes into this particular region, the learning will stop, almost stop. So you won't learn anything, so the gradient won't flow. So this is an issue because you want to learn. So this is again a problem of vanishing gradient, because here the gradients won't flow backward. Almost derivative becomes almost 0. So this is why we try to scale it over with a factor. So if you keep on increasing dk, you will this scaling factor 1 by root dk, it will try to bring your q dot k transpose values over a particular range, so that your gradient doesn't become too close to 0. Your derivative doesn't become too close to 0. So that's the issue, and that's why we scale with root dk, and this is the reason mentioned in the paper itself. So this is how we work with self-attention. We haven't worked on multi-headed attention as of now. Now let's go to multi-headed attention, and after that we'll see what's cross-attention. And then we'll go to the code. So now let's go with multi-headed self-attention. Now earlier what we were doing, we were using this entire q, we were using this entire k prime, we were using entire just v prime for the calculation of tension. Now in the paper it suggests that instead of using this entire thing, you break it down and then you apply the same formula of attention over the smaller chunks. So what they did, now this is my q prime, they break it down along the column by dk. So suppose if I had to say there are n heads, in paper they said number of heads were 8. Now your d model was 512. Now if I'll bring this entire 512 into 8 columns, so each column's dimension, which becomes dk, it will become 512 divided by 8. Now why I have used this double divisor? Because this should be an integer. So this is an assertion check which we generally used to do first, that your D model is exactly divided by number of heads. So it will become what? 8 6 48 32, 8 4 32, 64. So this DK becomes 64. So what we do after this? Now this entire DK is 64 64. So what we do? We calculate attention along these lines. So from the query Q prime, we take the first 64 column and this entire rows. This is rows is sequence length basically. Entire row. Then from the key prime we take first 64 column. Then from V prime we take first 64 column, and then we calculate one attention. So if you see these pink lines, they are coming from the same, and this is your attention one. If you see this blue line, these are coming from this this middle block, and then again blue line, and then this is attention 2, then green line, then this is attention 3, then this orange, and this is your attention 4. So you get 4 different attentions using the same formula. The only thing is that here the Q will be the dimension, here the Q will be of dimension sequence length cross 64 in this particular case. So done with it. Now you have your multiple attention over here. What you do, you will concatenate it along the dimension, as simple as that. This is it. Now this is still there is one more thing. So you have an X, you projected it using a linear layer. You have another X, you projected it linear layer. You have another X. I mean, these three are the same X. You projected it linear layer. Now you have an attention output. Now finally you will project it through another linear layer called W. It's cool. So this is what this is. Again, this is sequence length, and this entire thing, this DK. When you will concatenate it, it will become D model. So this WO will turn out to be a matrix that will again belong from R. D model cross D model, and when you will multiply it, this is sequence length cross D model. When you will project it using D model cross D model, you will get your output will come out to be will belong to R sequence length cross D model. So you see the consistency of dimension, it is maintained. So you have an input of sequence length cross D model, and you are getting an output of sequence length cross D model. So that's how multi-headed attention works over here. So one thing to focus is that in which dimension we have applied softmax. That was important, that I didn't find in any of the relative blocks. So that was one thing to notice over here. And then why we are scaling with 1 upon dk. Rest other it is explained in every other video about calculating multi-headed attention in a much prettier way. Now we'll come to cross attention. So now let's take a look at the cross attention. Now as we have discussed earlier, what does cross attention basically do? Cross attention takes two different modalities. One is something, let's say image, another one is text. This one I'll be explaining with a little bit of reference to the diffusion paper. Diffusion paper, what is that? Denoising through probabilistic diffusion model, TPM paper, or stable diffusion. So I'll be explaining a bit with taking a reference to that. So it doesn't work. So now earlier we had query, we had key, we had value, all coming out through same input. Now here, since there are two modalities, we'll have to assign something, like we'll have to merge this second modality. Let's say the first modality we were working on text, like sequence to sequence mapping. It was a vector of 77 cross 768, and now we have an image. Now image, we brought it into, we use some encoder to bring it into latent dimension, and then we just came to modify the image using something called, let's say, condition length and decondition model. So I have X, which is same sequence length cross D model, same as earlier in self attention. Now I have a condition. So let's say I have an image and I had a text. The image is of a cat, and the text is something like make this cat wear a hat, something like that. This is the condition. So at the end of the day, I want that cat output will be the cat wearing a hat. This is my intention. Now I have to somehow tell this information to whatever model I'm applying. I have to tell this information that this is your image vector, this is your text vector, and this I have merged over here, and you have to figure it out, like what's the relation over there. So that's where we use cross attention. So we had X of sequence length cross D model, and then we have this condition, text condition. Let's say this condition I'm representing with C, and this condition is belonging to something called R. This is some different dimension, condition length cross dimension of condition. This is some other dimension. This has nothing to do with sequence length and D model. So instead of query, I still have X. Instead of key, I have now condition, and value also I have made as condition. Now this architecture, this particular assignment of query key value, this is something I'm taking from the stable diffusion paper. So in this they do the same thing. But what I personally feel is that you can exchange this query and key. I mean, you can assign it to any of the thing as long as the dimensionality matches. You can assign one of the modality to query, the other of the modality to key and the value. Doesn't matter. So I have taken these things, and now this WQ, since I have not changed anything, so it will have the same dimension, D model cross D model. Now this WK dimension and WV dimension will change because I have to multiply this thing, right? So I have to project. So my first dimension of this projection matrix should be of D condition. Then only I'll be able to project it. Then I will this transformation W transpose X plus B. This transformation I'll be able to apply only if I have this particular. So in this, I think PyTorch doesn't use transpose, so it is basically WX plus B. So this transfer to apply this transformation, I have to make the dimension of W such that this multiplication of matrix multiplication can take place. So this, the first will become D condition, and the second one dimension will become D model, because again I have to do a matrix multiplication over here. So to maintain these consistencies, this is the dimension which I have to take for the projection layer. Now what happened when you do? So what's the dimension of Q prime? Q prime will be sequence length cross D model, will belong to, well, I have to write it more mathematically. So Q prime will belong to R sequence length cross D model. What will dimension of K prime? K prime will belong to basically R condition length cross D model. And similarly, the V prime will also belong to R condition length cross D model. So you got these two matrices, and then again the same thing, nothing different than cross attention. You have to do just you have to apply this softmax activation function, QK transpose divided by DK, apply softmax, and then multiply it with the V. You will get this attention. Now let's see what the dimension of this particular attention it's coming out to be. Now when you take QK transpose, your this particular after application of softmax, your dimension will be something sequence length cross D model. Okay, I think I might have messed something out here. Condition length cross D model. So if you do sequence length cross condition length, this will be the dimension after you have applied softmax, and then you have, this is basically QKT transpose by root DK, and then application of softmax. After this, you'll get a matrix of dimension this, and then you have to multiply with V. V is your condition length cross D model. So when you will V belongs to condition length cross D model. So when you will multiply this both, you will get finally the output, which will be again sequence length cross D model. So you can again see the consistency is being maintained. The input consistency with reference to the query. So you gave a query of sequence length cross D model. You wanted an output along the same dimension. So you got an output around same dimension of sequence length cross D model. But in this, you have taken consideration of V and K transpose itself. So two different modalities, two different matrices coming from these two different modalities, and you have merged it. I mean, you have calculated dependencies among what's the dependencies. Now I had a pretty good example of a real life example of what this self and cross intuitively means. So you can consider making a pizza. Now this is the example. I mean, it's completely random, out of nowhere. So you can consider the example of making a pizza. So if the references which you are taking, so you know the recipe and everything, so you are taking references from yourself, that okay, this is my now I have made a base. I don't know how to make pizza, but just I'm telling. So I had a base, and then I want to add some cheese topping over here. So what should I do? So you are taking references from itself only. So you have that particular knowledge, and you are just trying to find out the dependencies, that after this what I should do. If this is the thing I have done, so what is the probability that I should do this one? So you are taking no references from anywhere. Now what happens if you don't know the recipe of the pizza? So you will call your mom. Best advice ever. You will call your mom, and then you have some queries that I have done this. What should I do this? So what your mom will probably do, just an example. So we'll have a thing to check with that. Okay, this is done, this is done, this is done. So we'll have a list that this is done, this is done, this is done. If this is done, what I have to do next? So this particular list, it's key. When the query and the key matches, you return the corresponding value. That okay, this have matched. Now this is the value which you want to retrieve. Basically happens with most of the databases out there. So this is a pretty vague example of how query, key, and value, what's their intuition over. Some examples over there. So this we have learned about cross attention itself, and then we'll go through the code walkthrough and we'll try to relate how this linear projection matrices work over there. So in this, we'll try to, we'll go through the implementation of the transformer module. So this is pretty much in PyTorch. So I'm assuming that we are all familiar with the PyTorch in itself. So these are the three of my hyperparameters, the number of heads, the D model, and the D condition. So as I've mentioned, like when you see D condition, a different modality, so you can assume that this one we are implementing the cross attention section over here. Self-attention is pretty much simpler and it's much more easier because there you don't have to worry about the condition thing. Now after that, I have this my four layers, four projection layers, the Q, K, V, and at the end, I'll also have my output projection. So this one, this attention will get through the output layer to be projected over here. So these are my four projection layers. Then this is a simple function to calculate the tension. So since we are implementing multi-edit attention, so it's pretty much realistic and it's much more simpler if you can define a attention in a separate function so that it can take the query key value and the decay. Decay is the scaling factor, scale dot product attention over here. So this is like you are multiplying Q and K, QK transpose, and then you are calculating the attention. Attention is basically you are first taking the softmax of QK divided by root K, root DK. So you are taking this, you are calculating the softmax, and then you are multiplying matrix multiplication with V. So this one. So this is your attention, and it will get returned over here. Now let's go to the forward function. So forward function is something first of all, like I have this x and then I have this condition. So as we have discussed that x will be projected by using q and then condition will be projected using k and value. So k prime will be coming out of uh, k prime. Yeah. So this is the query. So query it is coming out of x. So x is getting projected using the q query and then condition is getting projected using key and the value thing. Now, X is basically we are taking a reference from the stable diffusion again. The X is an image basically. So what we have done, the first parameter is batch size. The second parameter, we have compressed, we have multiplied height and width, and this is D model. D model is basically 512, which was mentioned in the original paper itself. After that, what we are doing, yeah. So this all, and then condition is again this condition. Condition dimension is of sequence length cross D model. So after doing all this, this is pretty much consistent with the slides with all those things over here. So this is how we are implementing over here there itself. Then we are calculating the batch shape and the sequence length, which is not required as far as I can guess. Then dimension of it is basically D model divided by number of it. So the number of it, if you're giving 8, which was done as in the paper, so your basically dimension of each head will be coming out to be 64. That is 512 divided by 8. That is equal to 64. Now, what this chunk torch dot chunk is like it basically it is doing this splitting. This chunk it is creating this chunk out of Q, K, and V. So these all four chunks they are uh, they are coming out of the key chunk, and then you can iterate over these tuple to get in each individual chunk. So torch dot chunk takes a tensor, which tensor you want to create chunk, and then how much chunk you want to create, and along which dimension. So if you see in the key over here, we are having batch size, sequence length, D model. So we have to create chunk around this D model. So this is sequence length in the key section. This is your sequence length. This is your sequence length, and then along the column, it is your D model. So we have to create the chunk along D model, which is dimension number 2. So this is 0, this is 1, this is 0, this is 1, and this is 2. So we are taking K prime, we are taking now how many chunks we have to create, the number of heads we are having, that is 64. So we have to create 64 chunks and then dimension is 2. Similarly, we are creating chunks of query and we are creating chunks of value. And then simply multi-edit attention. I'm creating an empty tensor of batch, sequence length, and D head. So the thing with empty tensor is it initializes it something with default 0. So like if the first time you are going, you have to, I mean, so what it will do is like if I do toss.tensor, toss.tensor, let's have subdimension 2 comma 3. So and I'm storing it into X. So by default, X will be two rows and three columns, 0 0 0 0 0 0. This is the value it will by default assign it. Now I'm iterating it. So I'm taking the index in Q, K, V are coming from query, key, and value chunk. So for each iteration, this will come and get it stored into small q. This will come and get it stored into small k, and this will come and get it stored into small v. Now I'm calculating the attention, the function q, k, v, and d head. Now if I is equal to 0, like if it is my first time iterating over here. So if it is my first time, I'll simply assign my empty tensor with the attention whatever I have got over there. So if it is my first time over here, so I'll assign it with the multi-rate attention and then I'll continue it. Otherwise, I'll keep on concatenating along the dimension is equal to 2. Dimension 2 is basically again this dimension. D model. So as you can see in MHA, we are concatenating around D model dimension. So I'll keep on concatenating around D model dimension, and then at finally before returning, I'll project it again over using my output projection layer, and then I'll return my total attention. To test this, let's simply run it, and then we can just run this. In this, I'm creating a X. X is basically your input and then condition. And then you can see this is 64 cross 64. This dimension can be anything and then 768 and then transformer layer. Transformer, I'm defining that D model is of 512 and then D condition is of 768 and then a number of it. It's basically D model. Then we have D condition and then we have number of heads. Now, if you'll run this, you'll get this. I'm getting 4096 cross 512. Now, this 4096 is basically 64 cross 64. So, as you have seen in the explanation itself, if your X, that is the query dimension of size sequence length cross D model, the output was also coming out to be of sequence length cross D model. So here the sequence length is of 64 cross 64 and then D model is 512. So you can see the output is of sequence length cross D model. And this implies that consistently matrix and dimension wise it is maintained. And this is how you go on implementing with the transformer. One other thing that I would like to bring your attention to is the application of softmax. So if you see this is nn.softmax dimension is equal to 1. Dimension is equal to 1 is not that like in the slides we discussed that we apply the dimension along the in slides we mentioned that we apply the softmax along the dimension 0. Dimension 0 is basically row wise. But here I've written dimension 1. Dimension 1 is written because your this entire dimension includes something like this in PyTorch. This is first of all batch size and then you have row and then you have column. So if you have to apply the softmax around row in the dimension of the row, so you have to use dimension 1. Dimension 2 will become column. So that's one thing. Don't get confused that I applied over here like using column wise. So that's pretty much about the code walkthrough, and I hope it's clear and pretty self-explaining in itself.